All right, you guys hear me okay?
Yep.
All right, excellent. I'm a little different today. I'm actually broadcasting from home today, so it's kind of nice. Didn't have to be in today. All right, folks. Couple things I want to do. I anticipate this is going to be pretty much our last lecture for the semester. So really, we just have this. We have tomorrow's lab to finish up and check out, and then the final exam. So we're going to try to cover pretty much what we have to do today. All right, so couple things we'll deal with. We want to finish up this example problem that we were doing, which was a potentiometric titration problem. And then I want to go back and just recap a few calculations for the lab that we need to do. So we've kind of gone back and discussed that, and we'll review the chemistry real quick and then kind of talk about the calculations you're going to need to do to finish out that lab based on what you get tomorrow. All right, so going back and just real quickly reviewing this problem that we were dealing with. So it looks like we had a solution that contains a certain concentration of chloride ion, and I'm titrating that with a known concentration of silver ion. So part A was to determine the equivalence volume or equivalence point of the silver ion. So we found out we needed 34.97 milliliters of silver ion to be able to hit the equivalence point. So that's where the moles or millimoles of the silver are equal to the moles or millimoles of the chloride. All right. The reason we did that is because the problem setup depends upon where we are in the titration. Are we before the equivalence point, at the equivalence point, or beyond the equivalence point? So part B dealt with calculation of a cell potential prior to the equivalence point. Okay, so we saw that as we added the titrant, we ended up making solid silver chloride. So basically we had to work this as more or less a limiting reactant kind of problem, and then determine based upon how much silver chloride we made in the presence of silver, or sorry, in the presence of chloride ion, we set it up as a dissociation of the silver chloride to give us the silver ion back. And that was the source of our silver ion, which the electrode potential was responding to. Okay, so part C put us at the equivalence point. That was nice because the moles of the chloride were equal to the moles of the silver ion, as they should be. And we didn't actually have to calculate any concentrations here because basically the only thing we had in solution was solid silver chloride. So we just set it up as a simple KSP problem where the salt is actually dissociating in the presence of neither common ion. So we didn't have to worry about calculating a concentration. A concentration of the silver ion comes right out of the KSP calculation, as we showed. Then once we had the silver ion concentration, we stuck it back into our equation for E cell. All right, so finally part D was what's E cell after 40 milliliters of the titrant had been added. So this is going to put us beyond the equivalence point. Okay, so things actually get a little bit easier here because when we're beyond the equivalence point, we know that the Ag1 plus is going to be in excess. So the nice thing is when the titrant goes into excess, we really don't have to calculate an equilibrium problem out, okay? I'm not saying that no silver ion comes from the dissociation of the silver chloride we make, but the assumption we make is that once the silver ion goes into excess, the amount of it that we have from the titrant is going to far be in excess of whatever tiny amount is going to come from the salt. Okay, so generally we would just neglect the dissociation of the salt in this case. So let's just verify that we got this. So let's calculate the moles of each thing because ultimately I'm going to need a silver ion concentration. So I will need to calculate it a diluted concentration here. So I've got moles of Ag1 plus. All right, so I have my volume of it. I'll just convert it to liters here. I think I might have done it in milliliters and millimoles last time. I'll do it in liters and molarity this time, just for grins. You can do it either way. All right, so liters will cancel with liters. That's going to give me moles. So we're just verifying here that the silver ion is going to be in excess. I get 0.123732 moles of silver ion. Okay, so that's the moles of silver ion I have available to me. The moles of the chloride, remember, don't change, right? Because that's what's in solution to begin with. So we had that from a prior calculation, and that turned out to be 0.00064 moles. All right, so we verified here that indeed the silver ion is in excess. I've got more of it in there. Now, at this point, what I can do is kind of figure out how much of it I'm going to have in excess. All right, so probably the most complete way of showing this is to show the formation of the salt like we did before. So in other words, we can take our silver ion that we've got, let it combine with the chloride ion that I've got, and we'll let it go to AgCl. So in other words, this is going to show me what amount of excess silver ion I'm going to have. So again, that's 1 over a KSP, so that's going to be a large number. It's going to go 100% to the right from the standpoint of K. All right, so I can do an ICF. Now remember, in an ICF, I can use moles or molarities. I've got moles. We'll go ahead and stick those in there. All right, so from up top, I have 1,23732 moles. Chloride is 0.00064 moles. Okay, and all of my limiting reactants getting converted to silver chloride. We don't care about silver chloride. It's not in the law of mass action. Okay, so chloride, obviously, I've got fewer moles of it. That's going to be my limiting reactant. Looks like I have 6,4 there. Okay. All right, so I'll have no chloride in there. The difference between the silver, that's going to take me out to 0.123492. All right, so now I've got the number of moles of silver ion left over. Okay, so that's in excess. Now I need to turn it back into a concentration because that's what goes into my final equation with the Nernst equation inside of it, right? So what do I need to do to calculate the concentration of the silver ion I got left? Well, that's going to be the moles of it. Divided by the total volume in liters. All right, now let's go back and think about that. So I just added 40 mils, right? And I think I had, what, 25 mils of the solution to begin with in the beaker. So that's going to take me, what, 65 milliliters, which is 0.06500 liters. Okay, so that's my V total, just to remind you guys. So I'm just adding those volumes. And I'm going to end up with 0.00142 molar. Okay, and that's silver ion. All right, so now what do I do with it? Well, remember, the electrode is responding to the silver ion concentration in solution. So we have an equation for that. Okay, so you'll go back and remember, we're using the same equation every time. So E cell is going to be the Nernst equation, of course, for the cathode, which is the thing that's responding to the silver ion. So you'll remember from the prior parts of the problem, that was my E0 for my couple, minus 8.314. This part doesn't change, times 298. That's my temperature. 1 electron being transferred. Faraday is 96,485. Okay, so all that turns into volts, times the natural log of 1 over the silver ion concentration, if you'll remember. Okay, so that's your 1 over 0.00142. Okay, that's a 0 there. And then remember, I have to subtract from all of that the potential of the anode, which is going to be my reference potential, which is my silver-silver chloride reference, which is 0.197 volts. So again, nothing's really changed here. The only thing that changes is just the concentration of the silver ion I put in there. All right. So if we go and work all this out, and again, if you want to check your math, I think that all of this stuff here, as I have it worked out, turns out to be 0.168 volts. Okay, so 0.799 minus 0.168 minus 0.197 takes you to 0.434 volts. Okay, I think it's only good to that second sig fig there. We can double check that, but I think that's right. All right, so basically we can see again that the cell potential is varying depending upon the silver ion concentration. So let's go back and just take a look at where we were in terms of a cell potential all the way through. Okay, so part B which was before the equivalence point, had me at 0.157 volts. The equivalence point had me at 0.314 volts. And prior to the equivalence point had me at 0.434 volts. So you can kind of see what's happening here. I'm getting an increase in voltage as I go to higher and higher silver ion concentrations in the solution. Okay, so in the end, what you're going to end up getting is something that looks pretty much like a regular old titration curve. So if you were actually to plot it, and I'll just sort of eyeball it here, okay, and you're plotting E cell instead of pH, we'd normally plot pH or something like that, as a function of the volume of the titrant, what you're going to get is something that looks like a regular old titration curve. Okay, and of course, you know what to do. You're going to find the point of steepest slope in the titration curve, and then you would come down to the volume axis here, and that would give you your equivalence volume, just like it would in any other titration curve that we've looked like. So it works just like a pH titration curve in that sense. Okay, so basically this is how I can use an electrode and an electrode potential that I can measure to generate a titration curve and get back to essentially an equivalence volume, just like you would in the case of a pH titration. It's really no different. I mean, when you're actually doing a pH titration, you're actually measuring an electrode potential there as well. It's just that that electrode potential is sensitive to the concentration of the hydronium ion in the solution, as opposed to the silver ion in solution. It's basically the same idea. All right, questions, guys?
Well, one thing you said was that it's just like an acid-base titration, but we don't have any situations where we have anything like the conjugate action going on where our point of like steepest slope. Oh, I got myself confused. I was thinking pH 7. It's still gonna be that our point of inflection for no matter what is our equivalence volume, correct or no?
Yes, you got it. You got it exactly.
I got myself confused. Sorry.
Yeah. But that's okay, because in a sense, I mean, a lot of what we're dealing with it has to do with equilibrium and common ion effect and all these kinds of things. So all those kinds of things go into dictating the shape of the curve. But really, yeah, it's pretty much the same thing. So yeah, it's kind of an interesting take on a titration. So I don't know, I kind of like it. I think it's kind of neat. All right, so what I want to do now is I just want to go back and real quickly, because I just happened to be there and I was looking at it, go right way back up to the beginning of pretty much what I would say this chapter, where I was kind of going back over the chemistry of the experiment we're doing in the lab. So it's way up here. Yeah. And I just want to remind ourselves of what we got going on in terms of the chemistry here. Okay. So remember what it is we're trying to do. All right. Ideally, what we've done is we formed a precipitate. All right, and it's all sort of up here. Week 1 is standardization of the titrant. So here's the reaction equation. All right. Now I'm going to show you that the mole ratio that we need is 5:2, and you guys are going to go back and verify that for me. Okay, because I'm going to need that mole ratio a little bit later. So 5 moles of C2O42 minus to every 2 moles of permanganate. That's a redox reaction you got to balance, and that should be in your notebook, in your pages, so I can see that you guys know how to balance it. Okay, but I'm going to give you the mole ratio there because we're going to need it. Okay, so that was the redox titration that we used for the standardization of the titrant. All right, what happened in week 2? That's what you did last week. Well, we ended up forming a precipitate between calcium and oxalate. So that's what's in the bottom of the beakers that you guys are going to come in and analyze tomorrow. Okay, so that's the precipitate that's sitting in your beaker right now. So now what we're going to do tomorrow is we're going to take that precipitate and we're going to isolate it using filter papers. We're going to filter everything else out and clean it. So we're capturing the precipitate. Then what I'm going to do is I'm going to take the filter paper and everything in it, and we're going to redissolve that precipitate in an acidic solution. So we're going to free up the calcium ion from the oxalate ion. And then what I'm going to do is I'm going to take what we've got there and titrate it with permanganate. And this is going to be the standardized permanganate. Okay, so what ends up happening here is in the acid, the precipitate breaks up into calcium ion and oxalate ion. Okay, now take a note here. For every precipitate that breaks up, I'm getting one oxalate ion and one calcium ion, right? So it turns out I'm not titrating the calcium, I'm titrating the oxalate ion that came in with it, okay? So that's okay, because if I can get to moles of oxalate, do I have moles of calcium? Yeah, because for every oxalate that came in, one calcium came in from the precipitate. All right, so again, I can use the very same titration, but the same stoichiometry, 5 moles of C2O4 2 minus for every 2 moles of permanganate, to ultimately get back to the moles of the oxalate. Once I got the moles of the oxalate, I got the moles of the calcium. And from there, I can get back to parts per million. All right, so that's just a real quick recap of the experiment. But now what about the calculations that you guys have to do? So let's just spin down here real quick. It made sense to kind of just sort of review the chemistry going on before we talk about the calculations. So the first thing, and some of you guys may have done this already, is to calculate the concentration of the permanganate. That's what we do in a standardization. Okay, so we always have to start from the thing that we know about. So remember, you guys made a primary standard solution. It was made from dried sodium oxalate. Okay, so you guys took some volume of that sodium oxalate solution. It was around 1 milliliter or something like that. You metered it out with a micropipette, I believe. Okay, now you would have done this across several trials. Now, we want to get moles out of this. So you've got a molarity. So you can have some number, we'll do it in millimoles just to cut down on the number of calculations that we have to do. You can do it in terms of moles if you prefer, that's perfectly okay. Millimoles per milliliter of the C2O4. And the reason I'm showing this to you guys is because I'm not going to really have you around in class after this or see you in the lab. So you're going to kind of be on your own for these calculations. So I don't want you guys making mistakes that are going to hurt your accuracy and precision. So that's why it's important to get the calculations right. Okay, so I've got millimoles of the oxalate. I want to get to millimoles of the permanganate, but I know that mole ratio, right? For every 2 millimoles of the MnO4 minus, the balanced equation tells me I'm going to use 5 millimoles of the C2O4, 2 minus. Okay, so now that gets me to millimoles of permanganate. Now I want to get to a molarity. So the other piece of information I need here is the volume of the permanganate I used in the titration. That's going to go in the bottom. So 1 over some number of milliliters of MnO4. So look at what you've got now. You've got millimoles of permanganate over milliliters of permanganate, which is the same thing as the molarity of the permanganate, right? So you end up with some number of molar MnO4. Okay, so that's how you do the standardization. Everybody okay with that? You see where the numbers are coming from? I mean, you have to kind of fill in the blanks based on the measurements that you make and the answers you got, right? So this is your calculated molarity of your primary standard. That was sodium oxalate, right? Okay, so that was what you did basically on week 1. Okay, so now what about the analysis part? What's your goal in the analysis? Your goal is to get ppm, or parts per million, of the calcium ion in the solution that was given to you in the unknown. Okay, so remember that parts per million of calcium could be expressed 2 ways. I could say it's micrograms of calcium ion per milliliter of solution, or I could say it is milligrams of calcium ion per liter of solution, okay? And when I say liters, I mean liters of unknown or milliliters of unknown, all right? So remember, that's something else that you did. You measured out a certain volume of your unknown per trial, okay? So that's also in your notebook. So now we're going to start again from the thing we know. But remember, we standardize the titrant. So we know the concentration of the titrant. So we're going to start from the perspective of the titrant. So you're going to take some number of milliliters of permanganate that you've used in your titration, right, to get to the equivalence point. Okay, and then you're going to multiply that by the concentration, which is millimoles of permanganate per milliliter of permanganate. Okay, so that's what? That's the molarity of your titrant. That's what you did in week 1. Okay, so now I want to get back to the oxalate, don't I? So I'm kind of working in reverse here. So I know that for every, what, 2 millimoles of MnO4, I've got, what, 5 millimoles of oxalate. Okay, now we have another mole ratio we got to slide in here. Okay, because it's the calcium that we really care about. So remember, permanganate's reacting with the oxalate, but it's not the oxalate we care about, it's the calcium we care about. But remember where they came from. They both came from the precipitate, 1 calcium per oxalate. Okay, so I can say I've got 1 millimole of calcium ion per, we'll say 1 millimole of oxalate. They both came from the precipitate in that mole ratio. Okay, everybody good with that? We'll come downstairs here. So now I've got it in terms of the analyte, the thing I'm looking for, but now I got to get to parts per million. So I need to get to mass. Okay, so I can use my molar mass here. I can say that for every 1, let's see, I'm going the wrong way. For every 1 millimole of calcium, I've got 40.08 milligrams of calcium, right? Right, milligrams per millimole is the same thing as grams per mole. Everybody see that? So now I'm almost there, aren't I? I've got the milligrams part, so I've got the whole numerator of parts per million there. I just need the volume part in the bottom. Okay, so at this point, you know that you had some volume of your calcium solution that you used. So again, you measured that. Okay, so I forget how we did it, but you guys measured it, probably again with a microburette. So it looks like we got here, I'm just going to put 1 over, keep it in milliliters because that's how you measured it. And that's your unknown. And then we can convert that into liters because ppm is milligrams of calcium per liter of solution. So let's see, we got 1,000 milliliters of unknown per liter of unknown. So now if you look at your units, if we did it right, we're going to have milligrams of calcium per liter of unknown solution. That's parts per million, isn't it? So that's going to give you your ppm calcium. Okay, so again, I think you guys kind of all knew how to do this, but I want to make sure we're all on the same page about it. Because again, I'm not going to be seeing you at the time you guys are going to be getting this all done. So obviously you can ask me about it and I can help you with it. But if you don't do that, you give me the wrong calculations, then it's kind of on you if you have a crappy accuracy and precision because you didn't do the calculations right. All right, so do they make sense? And I'm kind of thinking, you know, the folks that I probably need to be preaching to probably aren't here. So.
Probably.
Yes. So you guys okay?
Yep.
All right. So making sense? All right. That's what we want to make sure of. Okay. So next thing, let's just talk a little bit about what ends up happening between tomorrow and exam time. Okay. So let's just kind of lay out the rest of, well, I'd say the next week here, which is pretty much what we're talking about. Okay, so tomorrow, obviously, you guys are going to finish up the lab and check out. Okay, so you're going to get all your data. You're going to check out a lab. You'll be done with the lab tomorrow. Then you're going to have your information to go off and make calculations with. Now, the other thing you've got is your abstract. Okay, so I've marked up the abstracts. I have them here at home. I'm going to bring them with me tomorrow. And I'm going to hand it back to you at lab time. Okay, there's no grade on them, obviously, because you're just looking at my comments. So what I'm going to ask you to do is to go heed my comments, change your abstract, make the corrections I'm asking you to make, okay? And then by next Tuesday, I want everything done by next Tuesday. By next Tuesday, I'm going to put a Dropbox over on D2L for you to drop your final abstracts into. So everything after this, since I don't see you, is going to come into me electronically, because I think by the end of the week, you guys are supposed to be off campus. All right, so everything's going to come to me electronically. So I'll put Dropboxes over at D2L. And by the way, I'm going to send an email out outlining this and reminding you of it as well. So I'm just kind of putting it out here now, and then you'll get the follow-up email with everything in writing explaining what you need to do. So abstract, fix it. And the other thing I would say is proofread it. One thing I noticed on the first round, not for all of you, but for some of you, is that it was kind of obvious that people were putting words on paper, but not really going back and reading what it is that you wrote. So proofreading is always a good idea to kind of make sure that what you wrote is actually what you think you wrote. So checking for syntax, grammatical errors, spelling, all of those kinds of things, please check it. So make the corrections and then go back and read it. Make sure it actually reads the way you want it to read, okay? So please, 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 it's only a paragraph. Please, proofread your work before you hand it back in. All right, so abstract, that'll be in a Dropbox. And that'll be by Tuesday. Let's say midnight. Okay, so there's that. Now we also have the lab. Okay, so these would be your yellow pages or white pages or whatever they are. So again, I'm going to have those due Tuesday, so I'm going to also have to set up a Dropbox for those. We'll say also by Tuesday midnight. You can get them to me anytime. I'll set the Dropbox up probably tomorrow. So that way you guys can get them to me whenever you want to get them to me. And honestly, the earlier the better, because then I can just start grading them and starting to deal with accuracy and precision, and I won't get swamped next week during exam week. Okay, but you've got that amount of time, but if you want to get on it and have everything done by the end of the week before you start messing with exams, that kind of makes sense. So I'll have the Dropbox for you so you can stick it in there early. So obviously you're going to have to scan your pages and send them to me as a PDF, and we'll have them there as a Dropbox. Okay, so the abstract and the lab are the last two paper items I'm going to need to get from you guys. Then we have the final. It's a written final, written cumulative final, as you would expect. That's going to be on Wednesday. It's going to be given electronically, remotely, because you guys, again, are going to be gone. All right, it's going to be at, I believe, I've got it written down here somewhere, Wednesday, May 19th. That's dictated by the university, not me, at 3:30 p.m. Okay, so this is just following the university's final exam schedule as they gave it to me. All right, so it's going to be a 2-hour final. And then I'll give you like 10 minutes to scan and submit. And again, it'll go to a Dropbox that I set up on D2L. Okay, I'm sure with your other courses, you guys are well familiar with the idea of scanning your documents in a reasonable manner and converting them to a PDF and dropping them into a Dropbox. Everybody does that, right? Yep. Is there anybody who doesn't do that? Okay. Figure with most of your courses, that's how you're corresponding with your faculty members. All right, so that's how that's going to work. So again, I'm going to outline all of this for you in an email a little bit later, probably this week. I think you guys are the last class that I actually have to talk to about this by way of email, but I kind of wanted to lay it out for you guys so you knew what to expect in terms of deadlines and how to submit and what I'm looking for. All right, I think that gets everything. Is there anything else that we need to deal with or any questions about that? Again, I think I'm preaching to the choir here. But anyway, I figured I can say it and then it's out there, and then the folks who aren't here I can refer them back to this lecture. Questions? Comments? Concerns?
So with the final, is it just more problems or just questions from labs throughout the semester?
Both. So basically, the scope of the final, because remember, you've got a lecture component and you got a lab component. So in a way, a lot of the studying you're doing is pretty much the same studying you're going to be doing for your dynamics class, right? Because a lot of the kinds of problems we worked are very similar to kinds of things you did in dynamics in terms of the equilibrium that we've done and the kinetics that we've done and things of that nature, okay? But make sure you're also looking back at sort of typical lab calculations like standardization calculations and things of that nature. You know, I could ask you a question like that, okay? And also don't forget about the electrochemistry stuff, because that's stuff that I don't know whether you got to that or not in dynamics. You may or you may not, but this might be the only place you're seeing that. So make sure you're looking back over the electrochemistry stuff as well. But yes, the long and the short of is it could come from lab stuff that you did or calculations you did there. It can also come from lecture material. So it's a truly cumulative exam. Other questions, guys? All right, so suffice it to say, I'll see you guys tomorrow at lab time, 5 o'clock. And we'll get things finished, get you guys checked out, and we'll be on our way. All right, if that's it, I'm done, guys.
All righty. Have a good one.
All right, thank you guys for hanging in there, and we'll see you all tomorrow.
Dr. Richardson, I had a quick question for you.
Yeah, you can ask.
Really, are we having a quiz tomorrow?
No,
Okay, that's what I thought. Thanks.
no, we're jumping right into it.
See you tomorrow. Bye.
All right, see you then.